This is the solution to question 2a from homework 3. Since we are dealing with the topic of exact differential equations, that will be the first attempt. So we're going to let m of x comma y be equal to x plus sine y, and n will be equal to x cosine y plus sine y. And we're going to first confirm whether or not this is an exact differential equation by finding the partial derivative of m with y and the partial derivative of n with x, which is also cosine y. So because these two are equal, we have an exact differential equation. Well, being an exact differential equation, we can propose that there exists a function du, a function u, such that du is equal to 0. Now, if we compare this with the given equation, it should be obvious that the partial of u with x is equal to m, and that the partial derivative of u with y is equal to n. So we're gonna deal with this one first. Let's number the equations first, perhaps. That would be a good idea. This is 1. Let's call this one 2a and 2b. So from 2a, we have that by the fundamental theorem of calculus, this is going to be equal to the integral from sum x naught to x of m of t comma y dt plus some function of only y. Substituting the values of x of m into the integral, we have x plus sine y. And since we're integrating with respect, sorry, this should have been a t. We have to use a different letter. We cannot simply integrate with respect to x when we are evaluating the integral at x. So since we are integrating with respect to t, it's taken as a given that y is a constant. And that means that this is t squared over 2 plus t sine y from some x naught to x. This x naught has to be chosen in such a way that this function vanishes. In this particular case, that x naught can be 0, since in both cases we're multiplying by t. So what do we have? We have that u is equal to x squared over 2 plus x sine y plus some function exclusively of y. I'm going to call this one equation 3. We're going to do exactly the same, but now with equation 2b. We have that n is x cosine y plus sine y. Now from equation 2b, we have that u is equal to the integral from some y naught to y of n of x comma s ds plus a function exclusively of x. Plugging in values for the function in x cosine y plus sine y, nope, x cosine s plus sine s ds plus psi of x. So we're integrating with respect to s. That means that x is a constant. So we write x sine s minus cosine s, and this is evaluated from y naught to y, and once again we have to choose y naught in such a way that this thing is 0. Or a constant. Yeah, a constant should be good as well. So if we were to choose y naught equals to 0, that would make this one 0, and we're gonna make cosine 0 equal to 1. The reason why a constant is okay is because we still have a constant of integration, and that one can absorb any other constants. So that means that u is equal to x sine y minus cosine y plus 1 plus some function of x. This is equation 4. We compare equation 3 with equation 4. Let's take a look at equation 3 again. I have x squared over 2 plus x sine y. X sine y is a shared function. So x sine y minus cosine y plus 1. Notice how this part here is a function of y, so that could be my phi of y, and plus x squared over 2, this could be my psi of x, and I can always add a constant. I can say that my psi of x includes an extra constant in here. Okay, and I'm going to absorb this 1 into the constant. So I write x sine y minus cosine y plus x squared over 2 plus k. Now, since we have that the u is equal to 0, then that means that u is equal to a constant. I call that alpha. Okay, so again we could combine those two constants, and I can say that u is equal to x sine y minus, I don't need the u anymore, x sine y minus cosine y plus x squared over 2 is equal to some constant beta. Now the next step will be to confirm that this is actually true. So to do that, I take this equation and copy it into the new page. And we're going to differentiate with respect to x. course the right hand side becomes 0, the left hand side becomes sine y plus x cosine y dy over dx plus sine y dy over dx plus x. Factoring out dy over dx, and sending the remaining terms to the other side, and well, here we need to rewrite it in the form m dx plus n dy. So I'm gonna multiply by dx, and we get x plus sine y dx plus x cosine y plus sine y dy is equal to 0. And we can compare this with the initial equation, x plus sine y and x cosine y plus sine y. So we have confirmed that it is indeed a solution, albeit it is in an implicit form. I don't believe it would be possible to rewrite in an explicit form. And well, that's all.